Good afternoon. Welcome to yet another IEAGHG webinar on low carbon hydrogen. My name is Abdul Aziz. I'm a technology analyst at IEAGHG. We are meeting this afternoon to discuss the results of a study titled Blue Hydrogen Beyond the Plant Gate. This is based on low carbon hydrogen production pathways from oil and oil-based feedstocks. This study is by the Organization of Petroleum Exporting Countries, managed by IEAGHG and conducted by Element Energy. The Technology Collaboration Program on Greenhouse Gas Research and Development, internationally known as IEAGHG, constitutes an autonomous and independent framework within the International Energy Agency's network. Views, findings, and publications of the IEAGHG do not necessarily represent the views or policies of IEA Secretariat or its individual member countries. As a technological collaboration program of the IEA, our mandates include, but not limited to, the assessment of the role that technologies play in reducing greenhouse gas emissions, fund research into the development and deployment of carbon capture and storage technologies, monitor and model geological storage performances, and provide our members and policy audience and the public with independent technical inputs. This slide presents some of the flagship activities conducted by IEAGHG, but because of time constraint, I will have time to run through just a few with you. Firstly, IEAGHG has published over 350 studies covering a broad spectrum of CCUS value chain. And we do this by employing the best academic institutions and technical consultancies from around the world to undertake detailed techno-economic assessments of different technology options and how these cost effectively reduce greenhouse gas emissions. The two flagship conferences organized by IEAGHG are the Greenhouse Gas Technology Conference, which is coming up very soon, and the Post-Combustion Carbon Capture Conference. Dates will be announced for these soon as well. The International CCS Summer School, which runs over a 5-day schedule, covers every component of CCUS. The target group for the summer school include young scientists and researchers that include PhD students and early career researchers. I wouldn't be tired by saying that I've been privileged to have been a part of the summer school back in 2019 in Canada, and it is simply an incredible experience. And I will encourage research students and those in earlier career research to keep a watching eye on the IEAGHG social handles and website to apply for the summer school against 2023. The next summer school will hold later this year in Indonesia. The 16th Greenhouse Gas Control Technologies Conference is coming up from the 23rd to the 27th October 2022 in Lyon, France. This is a leading conference for CCUS for more than 30 years, and which is returning for an in-person attendance since 2018. This conference is hosted by Club CO2 in Lyon, France. We are expecting over 500 presentations across 71 sessions and 7 parallel streams, and points of discussions and subjects that will be discussed spans across advances in capture technologies, negative emission technologies, demonstration projects, energy and climate change policies, CO2 transport and infrastructure development. For more information about the GIGT 16, visit the IEAGHG website. This slide presents the IEAGHG membership. Our members have been pivotal and crucial in the successes of projects undertaken by IEAGHG and I would like to seize this moment to extend our utmost appreciation to all our members. We have the principal investigators of the study from Element Energy in the person of Connor O'Sullivan and Matt Wilson. They will be speaking to you and discussing the findings of this study. I'll be moderating this study. And this webinar is going to be interactive, so I will ask you to keep your smartphones very close to you. I will encourage you to post questions, keep your questions coming through. There is a small box on the webinar platform that will enable you to post the questions. So without further ado, I would ask you to sit back and enjoy the webinar. I will now ask Matt to come on board to speak to you. Thank you.
Thank you, Abdulaziz. Yeah, and Connor's got the screen up. So I'm just going to very quickly introduce things. So thank you for IEAGHG for hosting this webinar. We're very excited to talk to you today. My colleague Connor O'Sullivan will introduce himself in a moment. My name is Matt Wilson. I'm the principal consultant who led the study. If you just go to the next slide, Connor. Yeah, so just a very quick introduction on Element. We are a sort of zero carbon or low carbon energy consultancy working across the energy space, everything from industrial decarbonisation through to built environment, transport, smart energy systems, and hydrogen. Obviously, Connor and myself work across our hydrogen and industry activities related to this study. And we work for a range of clients, everyone from the public sector all the way through to the private sector. We are now part of the wider ERM organization, so certainly bringing a lot more services in terms of boots to boardroom sorts of thing, but still continuing to do many studies like this for IEAGHG. I think I'll hand over to Connor to talk through the presentation, and particularly picking up on the interactive element that Abdulaziz talked about at the start. Thank you.
Yes, thank you, Matt. Yeah, so good afternoon, everyone. I'm Connor, a consultant at Element Energy, and I was part of the team that helped deliver this project on the oil-based hydrogen production. So just to set the scene a little bit for why we conducted this study. So at the moment, we've seen the hydrogen economies previously had a number of false starts, but is currently undergoing quite a significant shift in momentum. We're seeing many countries and government bodies start to incorporate hydrogen into their sort of net zero plans, with the UK, for example, developing a UK hydrogen strategy and business model. So it's hopefully an exciting time for the hydrogen industry. However, just to currently, to take a step back and look at what the current levels of hydrogen production are at the moment, it's already a very large existing industry with over 100 megatons a year of hydrogen production, resulting in about 1,000 megatons of CO2 a year. This is primarily due to the fact that it is dominated at the moment by fossil fuel-based routes of production. So as you can see on the figure on the right, natural gas is the largest production route, followed by coal, with oil making up a very small fraction of dedicated production today, although there is some byproduct production that does exist. At the moment, hydrogen demand is dominated by industrial sectors, so this is primarily from refineries. However, there are also some sectors such as ammonia and other chemicals that also represent significant demand streams. So if we're now starting to look towards the future, there is significant potential for the hydrogen industry to grow, with demand coming from sectors beyond just that of industry. So there is potential demand coming from the heating sector, with the potential to blend hydrogen into existing natural gas grids infrastructure. From the transport sector, where hydrogen can be used in fuel cell vehicles primarily for heavy duty transport, and up to sort of large and long distance transport such as shipping and aviation, and finally for power generation, and this could be in the form of both hydrogen turbines as well as stationary fuel cell application. So as part of the study that we conducted, we looked at a global forecast by region and by sector. So there's a lot more detail about this in the report, but as you can see, going from sort of today's 2020 levels, we're expecting some growth up towards 2030 and then potentially a rapid expansion out towards 2050. This study, the primary objective of this was to conduct a techno-economic analysis of some promising oil-based hydrogen production technologies. So as part of this study, we considered 8 oil-based hydrogen production technologies, which were then subsequently shortlisted down to the 3 most promising for large-scale, low-carbon hydrogen production. So we looked at steam naphtha reforming, partial oxidation, and hygienic earth energy. And so those are the technologies that we will be discussing today. The report is available online at the IEAGHG, so you can get in contact with them if you'd like to know more details, and there's significantly more information available in that than we'll be able to cover in today's presentation. As mentioned earlier, we're aiming to use the platform Mentimeter, so you can join our interactive session by entering the code below. However, I will also be sharing a QR code, so later in the presentation, you'll be able to scan that, and that will take you directly to the presentation. So you can join via 2 methods. All interactions will also be anonymous, so don't worry about sharing your views there. In terms of where we investigated in this study, there were 15 countries analysed, and these were split to 4 primary regions, so North Africa, West Africa, the Middle East, and Latin America. We were comparing in the 2020s against a baseline of steam methane reforming without carbon capture and storage in the Netherlands, and in 2050 looking at steam methane reforming with carbon capture and storage. All the regions considered involved the OPEC member countries alongside the Netherlands and Brazil. The technologies we selected for each country, so we assigned 1 oil-based hydrogen production technology to each country. These were not prescriptive and were primarily just to get a range of each technology in each region. So there is potential that different technologies would be suitable in different regions, but this would be a recommendation for some further analysis. So if I now dive into some of the actual technologies we investigated, but first of all, considering why would you actually want to make hydrogen from oil? So at the moment, it's primarily dominated from natural gas routes. However, some of these processes can be adapted to run on oil-based feedstocks. So where SMR is currently dominates the existing hydrogen production, steam naphtha reforming is a very slight modification to this process, so requiring sort of smaller advancements in the technology development to operate this in a low carbon configuration. There's also, I guess, an abundance of oil feedstock likely to be available up until 2050, with large amounts of existing infrastructure that could potentially be repurposed, enabling potentially access to low-cost hydrogen in the future. We'll go into more detail on some of the feedstocks that can be utilised, but there is potential that utilising low-value or waste oil feedstocks could enable very low-cost hydrogen to be produced in the future. So here are the first 2 technologies that we considered. So the steam naphtha reforming. This is an adaptation of the existing steam methane reforming process. So it's currently an operational process. We've taken the configuration from the previous IEAGHG study from 2017, which looked at different blue hydrogen production configurations. So we've taken case 3 in this case, which has a capture rate of 90%. The only change we've made to here is that at stage 1, the natural gas feedstock stream would be replaced by naphtha. This configuration could utilize other light hydrocarbon feedstocks, so this would could include as well LPG as well. For the partial oxidation process, this is a slightly more flexible process, so you can use both light and heavier oil feedstock streams. So that ranges from natural gas all the way up to heavier oil-based residues such as vacuum residue. This process has previously been used for coal-based feedstocks, but we are primarily focusing on the range from oil. A range of feedstocks were considered in the study, but today we'll just be displaying an average of these results. One of the key differences for this process to highlight is that the heating process that you have in the steam naphtha configuration is not required. However, you do require a large supply of oxygen, so this is typically supplied by an air separation unit, which you can see in the sort of bottom left of that process diagram. The process configuration that we've utilized is based on the Shell gasification process for blue hydrogen. The final oil-based technology that we looked at in this study in detail was the Hygienic earth energy process. So this is a significantly lower TRL than the other two technologies, and this is a process being patented by Proton Technologies, who are based in Canada. Essentially, what this process looks at, rather than extracting the oil from underground and then bringing it to a source of oxygen where you can combust it, you sort of reverse that process and you bring the oxygen to the oil. So in this process, you have an oxygen production unit above ground which you then use to pump your oxygen below ground. So that's the first stage. This results in a range of reactions in this in situ combustion process. So this will include processes such as oxidation, gasification, pyrolysis. But what this results in is very high temperatures which break down the hydrocarbons within the reservoir, which results in hydrogen rising to the top of the reservoir. By placing a membrane down into the hydrogen reservoir, you're then able to extract pure hydrogen from your reservoir, whilst keeping all CO2 emissions locked underground. So at the moment, this technology is at a demonstration phase, so currently at pilot scale. So within this analysis, there is a slightly higher uncertainty for this technology. However, it was included just to recognise the future potential for its deployment and large-scale production in the future. On this slide, we just wanted to show some of the key comparisons between the technologies. So if we just start looking at the energy demand in the top, on the left side of the graph, we've added the SMR as a comparison. So that's both with and without carbon capture and storage. As you can see, for the steam naphtha reforming, you're having a slightly higher feedstock consumption. And this is due to the impurities that are based within the feedstock streams of oil being slightly less pure, I guess, than the natural gas equivalent. Partial oxidation has a lower feedstock requirement, so slightly less energy goes into the process, whereas Hygienic earth energy will have the highest. However, typically this won't result in higher costs, as you will have your feedstock available on the site as it will be in the reservoir based on where you are producing. In terms of the electricity demand, you're seeing the highest partial electricity demand for partial oxidation, and this is due to the energy requirements to run the air separation unit. For Hygienic earth energy, for the base case we considered here, you're actually able to run all your electrical demand requirements on hydrogen processes. So hydrogen that you harvest at your well site, you're then able to use, generate electricity either via hydrogen turbine or fuel cell, resulting in no additional electricity requirement on site. So that's one of the benefits of the process. In terms of the captured emissions, you can see the red diamonds representing the capture rate. For Hygienic Earth Energy, you're seeing, well, 100% capture rate is assumed, as all CO2 will remain deep underground, and we're assuming no leakage. It's one of our assumptions, and we're getting a higher capture rate for the partial oxidation process than we are for the steam naphtha reforming. So you're getting lower levels of emissions from that process as well. So this is just a slide just to take a look at an overview of where each technology stands today. Currently, there are no known operations of steam naphtha reforming that we were able to find. However, the process is essentially identical to the steam methane reforming process, which is obviously commercialized and has there's some existing low carbon hydrogen production for the steam methane reforming process. Partial oxidation, this is primarily being developed by Shell as well as Air Products. However, we're currently unaware of any oil-based low carbon hydrogen production processes at the moment. However, we wanted to recognise that the flexibility of this could make it a potentially strong technology choice in the future, as you're able to use both light and heavy feedstocks with minimal pre-processing requirements. And the Hygienic Earth Energy process developed by Proton Technologies, currently a much lower TRL than the other technologies, but there is currently a pilot facility that is operational in Saskatchewan, Canada, and then this process will supposedly work with any hydrocarbon-based reservoir, so potentially offering significant potential to be deployed worldwide in the future. So I think at this stage, we'll go to our first mentee session. So if you are able to scan the QR code on your phone or join via your desktop by joining mentee.com and entering the code in below, then you should be able to access the first question. So just bringing up now, hopefully I'll start seeing some results come in and that will confirm it's working. But we just wanted to know which technology has the greatest potential for large-scale deployment in the future. So good to see some results coming in now, showing that it's working, showing steam naphtha reforming taking an early lead. Interesting, as this is obviously shares a lot of similarities with the existing steam methane reforming process, but as naphtha is, I guess, a refined product, is potentially will be very much dependent on where you can access low-cost naphtha in the future. Getting about equal for POX and HEE, so interesting to see some people thinking that we might see more HEE in the future as well as POX, but looks like SNR is taking the lead on that one. I'll just leave this running for a few more seconds, and then we'll be able to go to our next question. Okay, that looks like it's settled down. Oh, no, one more, but another one first. Okay. So then we just wanted to know, based on what the audience thinks, what share of global hydrogen production will come from oil-based feedstocks by 2050. So hopefully you'll be able to split this to a breakdown of 100%. And yeah, we're looking at the potential for oil-based blue hydrogen production by 2050. So seeing, I guess, initially green hydrogen being the dominant factor. I guess this is a lot of countries looking to, including the UK, looking to deploy large amounts of renewables, whereas others potentially looking at blue hydrogen as a transition technology. So natural gas-based blue hydrogen. Certainly in the UK, there are a number of projects in development. However, I guess recent rises in price of natural gas have potentially led to larger uncertainty in the future. So currently oil-based, well, certainly having a larger role than it does at the moment at 14%, but certainly significantly behind that of natural gas-based hydrogen and green hydrogen via, well, primarily electrolysis. So I'll just give this another few seconds. Okay, so we're looking at about a 50% split for green hydrogen, and then the rest, well, more natural gas than oil. So I'll switch back to the presentation. That should be running in the background there if anyone else is a bit slow on putting their results in. So to run through some of the techno-economic assessment that we did as part of this study. Again, we won't be able to go through all the assumptions we made. There's significantly more detail available in the report, particularly in the appendix section if anyone is interested in digging further into the details, but I'll just run through some of the highlights. In terms of the boundary conditions we considered, we split these into the gateways, as you can see in the top right figure. So gateway 1, considering the hydrogen production facility, gateway 2, including the CO2 transport and storage, and gateway 3, the hydrogen distribution and storage. We based all our analysis on the assumption of a 300 megawatt facility with a lifetime of 25 years, using a standard discount factor of 8% with sensitivities of 5 and 10% used as well. So this was primarily to align with previous studies done by the IEAGHG and also a parallel study that we looked at natural gas-based blue hydrogen production in the Netherlands. In terms of the technology readiness levels, as highlighted earlier, the HEE process is significantly lower TRL than both the steam naphtha reforming process as well as the partial oxidation. So we tried to make these as comparable as possible throughout the study. But we've labeled a few caveats throughout the report. The CapEx and fixed OpEx were based on a combination of literature reviews as well as stakeholder engagement. So we reached out to a number of industrials and technology developers during the study to make sure our data was as up to date as possible. And in terms of the CO2 transport and storage, we considered both pipeline storage as well as CO2 shipping. So the assumptions we made, again, are highlighted in the appendix, but this was very much dependent on region. Some areas have wider data availability for their geological storage potential. So we considered this where possible, whereas some countries would be heavily reliant on CO2 shipping even in the future. In terms of the hydrogen distribution and demand, in the short term, so in the 2020s, we were considering hydrogen distribution to the closest export market. So the primary export markets that we considered were East Asia, North America, and Western Europe. Whereas in the 2050s, we considered both export to these large hydrogen markets as well as local distribution to industrial users, where we're assuming that demand for hydrogen has grown to a sufficient level that you can distribute it to local industry. In terms of the variable costs we considered, we've provided the carbon prices forecast we've used. So we used a range of forecasts. So you can see the ones for the Middle East on the left, and all the others, excluding the Netherlands, which is higher than the rest, as well as the oil forecast on the bottom right. This was, I guess, accurate at the time that we did the analysis, but obviously due to recent climate, there's been some significant fluctuations that were not considered in the price of oil. So that is the forecast we've used, and there's more details about the assumptions, but it's primarily based between the EIA reference price and their low oil price. So the average of those is the central, and that was shown to fall. Well, the majority of forecasts produced by oil majors were shown to fall in between those limits as well. In terms of cost reductions up to 2050, we assumed learning rates of between 5 and 20%, and also cost reductions between CO2, TNS, and hydrogen distribution as economies of scale and technology developments advanced. So now just to present some of our initial results. What you can see here is the comparison for all countries for the 2020 case. So there's quite a lot to unpack here, but what you can see is that for all countries, oil-based hydrogen production is likely to be higher cost than the base case comparison, which is steam methane reforming without CCS in the Netherlands. So that one's shown on the far left of the diagram. What you can see is for all countries, the feedstock cost is a significant cost component. So that's shown in the light blue bar, whereas hydrogen distribution is also a very large cost, and this is primarily due to the long distances of hydrogen shipping to the areas of demand. So those markets in North America, East Asia, as well as Western Europe, for some countries represent significant shipping distances and therefore very high costs. The range of CO2 transport and storage is also dependent on which countries require shipping or via pipeline. However, for all countries, this is a relatively large cost component. The only region where it's slightly lower is in the Middle East, as you can see, where they are likely to have potential for onshore storage, which is likely to be much lower cost than offshore. One other thing to note here is that the Hygienic Earth energy process doesn't have a CO2 transport and storage cost associated with it. So you'll see that that's one of the key advantages of the technology, not having that green component associated with its levelized cost of hydrogen production. So if we now move to the base case comparison for 2050, we're now comparing against steam methane reforming with CCS in the Netherlands. However, we're still seeing at this stage oil-based hydrogen production in these regions being higher cost than this base case. So range of costs ranging from 30% up to 99%, HEE being the lowest cost option here. And again, this is due to one of the benefits of it not having a CO2 transport and storage component associated with it. What we do see though is as part of this analysis, we analyze the number of sensitivities. So if I just roll to the lowest cost pathway, you can see suddenly there's a significant reduction when we're looking at the lowest cost pathway. So some of the key assumptions here are that hydrogen distribution is now to local industry, so there is no longer shipping to the large hydrogen markets, so that is a significant cost component saving. But the other big cost component saving is for the POX and HE technologies, where low value feedstocks can be utilized. So in the case of POX, this is likely to be vacuum residues, which typically have very low value. And for Hygienic Earth energy, the idea would be to target depleted oil and gas reservoirs, which are no longer economical for oil production. However, there is still significant oil left within the reservoirs that would enable hydrogen to be produced. So typically, these reservoirs will become economical when around 50% or 60% of oil is still remaining within that reservoir. So there is still large feedstock available for hydrogen production, and this is where there could be significant opportunities for hygienic earth energy. For steam naphtha reforming, you'll see that the feedstock cost still remains high, and this is primarily because naphtha is a refined product and therefore is likely to still have high costs associated with it. This is potentially a limiting factor for the technology. However, in some regions, it still may be possible that low-cost naphtha is available. But to summarize, these very low-cost hydrogen are primarily driven by the fact where you can essentially get your feedstock for almost no cost. So that is where there is potentially a niche in the market for oil-based hydrogen production. So now we've run through some of those results from the techno-economic analysis. We'll go back to our mentee questions. So hopefully people are still being logged on. But the first question here is, will there be low-cost oil feedstocks available in the future? So hopefully we can see there's the availability going on the bottom and feedstock cost going along the y-axis. We're looking to see what sort of range of prices of feedstock we're looking at for oil. So whether this is realistic in the future. So ideally would be for hydrogen production, you'd be wanting it to be in that bottom right region where with high availability and low costs. However, equally, whether this is realistic, as you can see, we're seeing a huge range. So going up from high cost and low availability all the way to relatively low costs with high availability. So doesn't seem to be a clear agreement on this process. So I'll let that run for a few more seconds just to see if we get any more results in. But yeah, interesting to see the range there between okay. Okay, I'll move now to the next question. So now this is the same question that you were shown earlier, but we just want to see if the results have changed based on the results we've just shown you. So what share of global hydrogen production will come from oil-based feedstocks by 2050? I think previously oil-based hydrogen production came out at about 14 or 15%. Green hydrogen was about 50%. So it'd be interesting to see if those results have changed at all based on the information we've just shown. So initially it's looking to be fairly similar, potentially a larger role for natural gas-based hydrogen production. So I'm not sure if somehow green hydrogen production slipped down the ranking order, now about level with natural gas-based, but equally we're seeing a slightly higher percentage for oil-based blue hydrogen production. So I think going from about 14–15% up to 19% now. So interesting to see that some people maybe change their mind based on some of the results of the presentation. Okay, I think I'll flick back to the presentation, just conscious of time. So now looking at part of the life cycle assessment that was conducted as part of the study. So this was conducted by our partner CE Delft, who unfortunately aren't with us today, but they conducted a cradle-to-gate analysis on the three technologies that we've shown you. So this was a screening LCA, and it was primarily focused on the carbon footprint. However, there were other environmental considerations taken into account. The system boundaries for the cradletogate analysis are shown in the figure below. So looking from the point of oil extraction up to sort of hydrogen compression and CO2 storage, but not accounting for hydrogen transport. So just first of all, looking at the results produced in the 2020s. For all hydrogen production phase technologies from oil, you can see a significant reduction in the carbon footprint. So when comparing against the benchmark steam methane reforming without CCS, you're getting a carbon footprint of about 10 kilograms per kilogram of hydrogen, whereas you're getting a range of between sort of 1.3 to 5.5, depending on which technology and which region. For the steam naphtha reforming technologies, which are shown in the first third, you're getting a relatively significant carbon footprint associated with direct emissions, and this is primarily because the capture rate is lower, is the lowest out of all the technologies. So those are shown by the red triangles at the top of the figure. However, for both the partial oxidation and steam naphtha reforming processes, you're getting emissions associated with the feedstock as well. So this is fairly unavoidable when for these two hydrogen production technologies. So this will be dependent on how the oil is produced and transported to your production site, whether that be with naphtha, bacterium residue, or crude oil. And further validation on the carbon emissions associated or calculated in this study will need to be validated when deploying any oil-based low-carbon hydrogen in the future. In terms of hygienic earth energy, there is no emissions associated with the feedstock, as this is because your oil is essentially remaining underground throughout the whole process. The yellow bars do represent electricity from the grid. So this is the largest component for hygienic earth energy. You do, for partial oxidation, for hygienic earth energy, you're also able to operate the system utilizing hydrogen that you produce on site. So that is why the black bars show a range, as you're then able to essentially decarbonize your on-site electricity demand by supplying it with hydrogen you produce on site. Looking forward to 2030, the most significant decarbonisation that happens for a lot of countries during this period is due to the reduction in that yellow bar, so resulting in the electricity from the grid. And this is due to a number of the regions' electricity grids decarbonising during this time. For all technologies, a source of low carbon electricity is likely to be a key way of reducing the carbon footprint of the technology and the hydrogen produced overall. And again, this is a key benefit for the IEAGH process, where you're able to utilize on-site hydrogen generation with a hydrogen turbine. So just finally, to wrap up with a few conclusions before finalizing off with our final interactive session. This study established that in the short term, oil-based hydrogen production is likely to be costlier than any existing grey hydrogen production method without CCS, and also more expensive than natural gas-based blue hydrogen production. However, it has identified that there are pathways to competitively produce hydrogen from oil and oil-based feedstocks. So when compared to both natural gas or electrolytic hydrogen, there's much more detail about this in the report with a comparative analysis as well. For all technologies, reducing the CO2 TNS is a key factor in reducing the overall cost of hydrogen. So that is likely to happen over time, but further development is required. And for all oil-based technologies, were found to have a lower carbon footprint than existing steam methane reforming without CCS. However, it's key that there is further validation on this in terms of sourcing, ensuring that the emissions associated with oil production, as well as long-distance hydrogen transport, are validated in practice. In terms of some of the recommendations, it's required that there is further funding for FEED studies and pilot project deployment to ensure that these technologies can be deployed at scale. A key opportunity that we highlighted for oil-based production is the ability to utilize low-value feedstocks. So this is likely to come from either low-value or waste feedstocks being produced in refineries that could potentially be utilized for hydrogen production, or utilizing depleted oil and gas reservoirs for the Hygienic energy process. For all technologies, it's likely that shared CCS infrastructure, or primarily for the SNR and POX processes, will bring down the cost of hydrogen production. So that's looking to deploy them in clusters of other emitters. However, just to wrap up, there is further work needed to explore optimal technology deployment by region, and any future projects will need to have some sort of certification that will enable, I guess, the hydrogen carbon intensity to be verified before projects can advance in their development and hydrogen be transported to markets of demand. So just to now finalize by going back to our final mentee session. We wanted now to have a bit more of an open input from the audience. So wanted to see what some of the views are on what the implications of rising natural gas prices for oil-based hydrogen production. Potentially with rising natural gas prices, we'll see oil become more competitive. So yeah, that's one of the first answers. It's likely that there is going to be an abundance of oil availability in the future, and natural gas demand is going to be dominated from other sectors. So potential and opportunity for oil-based hydrogen. So yeah, a lot of similarity in some of these answers coming through, potentially showing that if natural gas prices are likely to remain high in the future, this could potentially be beneficial to oil-based production. However, also recognizing that oil-based hydrogen production may never kick off, and this may just accelerate the transition to more renewable-based green hydrogen. Another good point raised here about alternative decarbonisation pathways. So many industrial sectors may look to deploy electrification, replacing some of their processes, whether that be for heating or otherwise. So another good point about potentially oil prices remaining high as well, and potentially having some link with that of natural gas, potentially balancing out in the future. So oil-based production potentially being linked to that of natural gas. Okay, I'm not seeing any new ones come in there, so I'll go to our next one. So this is again, how will oil-based production compete with green hydrogen production in the future? So a couple of answers highlighting that it's likely that green hydrogen production will be the preferred solution for many regions. I think one of the advantages that oil-based production could potentially provide is that of scale. So some of the technologies are already relatively well developed, and there's, I guess, well-proven processes in place, and potential to utilize existing infrastructure. So there is potential that oil could provide low carbon hydrogen at a larger scale. So yep, so it could potentially be very much beneficial in these oil-rich countries. So likely to be very regional dependent. Hopefully oil may not compete with green. Yep, hopefully if we're seeing large-scale renewable deployment, we're going to be seeing significant reductions in green hydrogen production as well. There's one there about the Hydrogen Go certification scheme. So yeah, a key point about, I guess, any low carbon hydrogen production being able to qualify for the relevant schemes. Okay, and now just move to our final question. So this is very much on which countries or which regions we think oil-based hydrogen production is likely to be developed in the future. So whether this is, if people have any ideas where alternative hydrogen production methods from either natural gas or renewables may be limited, but there may be opportunities for oil-based hydrogen production. So the US highlighted early on, so obviously a big oil producing country at the moment, the Middle East as well, another clear favorite. Venezuela, yeah, so this was, they obviously have huge oil reserves as well, and just generally oil-rich regions. Apologies if anyone's seen that answer. Yeah, so I think, yeah, we've got a list here of West Africa, Gulf of Mexico, Brazil, West Australia, interesting, as certainly an area we haven't explored within this study.
Cool. Should we jump to the Q&A?
Yeah, so that is the last slide.
Brilliant. Well, thanks a lot, Connor. Really interesting stuff. I'm just going to pick up on a couple of the questions in the sort of the 5 minutes or so we've got left. So there's a first question from Ken around HE seems somewhat like a new version of underground coal gasification. Is this a fair comparison? I don't know if you've got any thoughts on that. Perhaps I can respond.
Yeah, no, I'm happy you to take that one.
Sure. So I think the answer is yes, and it's something where, I mean, as Connor flagged, it's particularly low TRL technology, and I think was it you that also asked? Yes, and you can also ask about whether HE is sort of green or blue. Obviously, it's something that one technology developer is particularly focused on, and it's something that at the start of the project we were quite interested in just understanding its potential. I think it is fairly similar to underground coal gasification. That's a fair comparison, and obviously we just need to make sure when it comes to managing the CO2 emissions, it's not a fracking exercise where you've got leakages of any sort of gases or unpleasant toxins or metals or anything else like that exist already in the reservoir or are escaping into water aquifers, things like that. I suppose the point behind the, the technology, excuse me, is that it is just about injecting oxygen into the reservoir, and so you're rather than fracking, for example, which is about injecting obviously a blend of chemicals and water into shale. So they're currently developing that, and hopefully we'll see if it has got legs over the next few years. I suppose you classify, the problem with the color classification gets a little bit tricky, I think, when you consider technologies like this, but I suppose depending on the feedstock, because of the feedstock, you consider it more blue than green. Question from Tor, why do all cases end with 90% capture rates? Is this a physical limit? Connor, I don't know if you've got any thoughts on that, otherwise I also have to pick that up.
Yes, I think this was just a primary assumption from the study. So for the steam naphtha reforming, it was based on the IEAGHG configuration. We considered the highest capture rate configuration for that for the process within that study. So that was 90% based on flue gas capture, so post-combustion capture. And then the capture rate for the POX process that was provided from a combination of stakeholder engagement as well as data from literature as well.
Great, thanks, Colin. There's another question from Ken, which I thought was a really important one, which was at the time, excuse me, at the time of when we'd got to this part of the presentation, about halfway through, we'd spoken on TRL, energy input, CO2 emissions, etc., but hadn't really picked up yet on the methane, and which is essentially just upstream emissions, which are obviously really important, and they were flagged in the LCA work that our colleagues at CE Delft did, or not colleagues, they're partners. And I suppose there are numerous studies that have come out recently around blue hydrogen that really flag the importance of monitoring the upstream emissions, because where they are not properly managed, the short-term impact on climate is significant, which goes to one of our conclusions and recommendations, which is that the certification process for those areas which are likely to progress faster on adopting hydrogen are stringent when it comes to fossil fuel routes, and make sure that any sort of upstream emissions are managed, so that projects that are currently in development around the world and looking for imports are not being lax in their fugitive emission management. So I think that's a critically important part, and it was well picked up. Question from Tamoya, would hydrogen with CO2 EOR be regarded as blue hydrogen? Again, I think I'll sort of put this to the fact that colors become quite challenging, and we're certainly hoping to go in the direction of more about CO2 certification by carbon intensity. So, for example, the UK has recently done a carbon intensity assessment that was saying less than 20 grams per megajoule of hydrogen 20 grams of CO2 per megajoule of hydrogen is deemed compliant with their standards, with the intent of pushing that down. I suppose with hydrogen, which is with CO2 EOR, technically you're storing the CO2, but it depends where you draw your LCA boundaries. And obviously, as soon as you start considering downstream use of those fossil fuels, how they're used, it might not be so clean in the end. So remains to be seen, I suppose. But we certainly didn't look at any technologies like that or the treatment of CO2 like that in this study.
Matt, I think we're running out of time. Yeah, very well. Yeah, very well. Before I bring this webinar to a close, I think with regards to the comment made regarding CO2 capture rate, I think IEAGHG have now moved away from from the norm of implementing 90% CO2 capture efficiency, and I think in one of the latest studies embarked by IEAGHG, obviously it was being very acknowledged that resin CO2 capture efficiency to up to 95 to 98 would literally be achieved with incremental cost increase. And I think we're promoting about 95% CO2 capture efficiency. This is indeed a very informative, very interesting webinar. I would like to thank our audience for coming on board and participating in the interactive session. The mentee tool has been absolutely instrumental in engaging with our audience. I would like to thank the speakers, Connor, Matt from Element Energy for coming on board. Thank you all. And so I'll see you guys very soon.
Thanks, everyone.
Thank you. Cheers.
Thanks, everyone.